Now let's talk about the motion of a charged particle in a magnetic field. And the basic idea is that we consider a single particle, and I'll assume that it's a positive particle, moving with velocity v in a uniform magnetic field B. And I'm assuming that there aren't any other forces acting. For example, the weight would be negligible. And this boils down to three separate cases. In case 1, the velocity is parallel to the magnetic field. In case 2, the velocity is perpendicular to the magnetic field. And in the third case, the velocity has components that are parallel and perpendicular to the magnetic field. And I'll call these components v parallel and v perpendicular. In the first case, with v parallel to b, when I solve the cross product, v cross b, it basically comes out to 0. When you evaluate the cross product of two vectors that are in the same direction or opposite directions, that result is 0. This is what the cross product gives you. You can actually see this from the other form of the equation, Fv is equal to qvb sine theta, because if the velocity and magnetic field are parallel, then theta is either equal to 0 if they're in the same direction, or theta would be 180 degrees if they're in opposite directions. And in both cases, sine of 0 gives 0, and sine of 180 also gives 0. So when v and b are parallel, the sine component of this, or the sine portion of this equation, goes to 0, and that means that the force, the magnetic force, is equal to 0. And then I can write that as a vector because it has 0 magnitude, and it doesn't matter what the direction is. The direction is meaningless when you have a vector of 0 magnitude. So this is kind of boring. What this means is, in terms of the motion, when you have no force acting on something, it comes back down to Newton's first law. The particle will just continue in a straight line with constant velocity. The second case gets more interesting when the velocity is perpendicular to the magnetic field. In this case, when you evaluate the cross product, v cross b, this boils down in terms of magnitude to vb sine of theta, where theta is now 90 degrees because the velocity and the magnetic field are perpendicular to each other. And sine of 90 degrees simplifies nicely down to 1. So in terms of the magnitude of the force, we get qvb sine of 90 degrees, which basically then is just qvb. Since the magnetic force is perpendicular to the velocity, therefore the acceleration will also be perpendicular to velocity. And if the acceleration is perpendicular to the velocity, then it can't be speeding up because the acceleration will not change the speed. It can only change direction. And after the velocity changes just a little bit, the force is going to be perpendicular to the new velocity still. So even though the velocity is changing direction, the acceleration is still perpendicular and the velocity will not change magnitude. The speed will still not change. So the charge, Q, will move in a circle at constant speed. And that's keyword for uniform circular motion. And hopefully you remember from uniform circular motion that the magnitude of the acceleration was equal to the speed squared divided by the radius, and also that the speed was equal to the circumference, which is 2 pi r, divided by the period, which is the amount of time it takes to go around one circle. The next step is to substitute these uniform circular motion equations into the magnetic force equation, where we can, and we'll come up with some interesting results. And again, you probably have figured out that when a physics teacher says something is interesting, it means it's a little bit tricky, but it's really not that bad. I would say the trickiest part here is to remember a little bit from mechanics with uniform circular motion. The first thing to do is to remember that the net force is equal to ma, the mass times the acceleration, from Newton's second law, and so then we can substitute that in, and we have the mass times the acceleration is equal to the charge times the speed times the magnitude of the magnetic field. Then we can take that acceleration from uniform circular motion and substitute that in, so then we'll have the mass times v squared over r is equal to q times v times b. And one of those velocities, or one of those speeds, is going to cancel out, so that we have mv over r is equal to qb. And from here it can go in two different ways. One thing I'm going to try is isolating r. So to isolate r, I need to multiply both sides by r and then divide by qb, and that will give me that r is equal to mv over qb, where mv is the momentum, and the momentum often has the symbol p. So the radius depends on the mass of the particle, the speed, and it also depends on the charge of the particle and the strength of the magnetic field. But a particle in this situation where the velocity is perpendicular to the magnetic field is going to travel in a circular path. The next thing to try is expressing the radius and substituting in the speed from uniform circular motion. So I would have m times 2 pi r over t divided by qb. Then a really interesting thing happens because we have r on both sides. The r cancels out. So I can isolate the period as m times 2 pi divided by qb. And if you remember from waves that the frequency is equal to 1 over the period, then I can just invert this to get the frequency as qb divided by 2 pi m. The third case is the most fun of all, where the velocity has components parallel to b and perpendicular to b. And remember, we called this v parallel and v perpendicular. In case 1, where the velocity was parallel to b, the velocity didn't change. And essentially what happens is that the v parallel component doesn't change. It remains constant. So the particle q keeps moving at a constant velocity parallel to the magnetic field. In case 2, when the velocity was perpendicular to b, we saw uniform circular motion, and the component of the velocity that's perpendicular to b actually undergoes circular motion. When we put these two things together, we get helical motion. And I'll try to draw this as if we're looking at it from the side. If we have a particle that's moving to the right and slightly down at some instant in time, and if we have a magnetic field that is pointed straight down, then the particle will describe a helical trajectory. And if we draw that out, we would get a helix. And so at that point in time, this particle will have a component of velocity that is parallel to the magnetic field, and that component doesn't change, that's constant. Then there's another component of the velocity that is perpendicular to the magnetic field, and it's the perpendicular component of the velocity that causes the uniform circular motion. One of the things that comes out of this is something called the pitch, and the pitch is the distance between two successive turns. I'll just make more space by moving the magnetic field vector a little closer there. D, the pitch, is the distance traveled parallel to B during one period. And since speed is distance over time, I can get distance by multiplying speed times time, which is why I multiply v parallel by t to get the pitch. In my experience, this has confused quite a few students on homework problems and the odd exam problem. And it's a really minor detail in a way, because we bring in some concepts from mechanics in terms of the kinematics of uniform circular motion for case 2, and then just speed being distance over time for case 3. And we really can't separate that, because the problems that you're going to see are going to talk about how particles move. And you really have to be a little bit on top of the kinematics to get the full marks on those problems.